Give me a second. All right, so today fine. So today's plan is to discuss the questions from humidity, past paper questions from humidity. Last week we discussed the basic theory concepts. So let's first of all have a look at those theory parts. So what we discussed last week at the last class actually. Yeah. We shared notes from last class. So this is what we discussed at the last class. We started with the definition for the class before this. The class before this, we learned the definition for absolute humidity, and then we started with the equations for relative humidity. Now, what is the definition for absolute humidity, people? Absolute humidity is just the density of water vapor. You divide the mass of water vapor by the volume of the chamber, volume of the area given to you. And then we learned the equations for relative humidity. There were 4 equations for relative humidity. These are the 4. So depending on the context of the question, we will be choosing the most appropriate equation. All right. And in addition to that, we did certain questions. We did certain questions about humidity, how we can use the equations we learned to find out relative humidity, and moreover dew point as well, because there were 4 equations we learned. Yes, and out of those 4, you can see first equation is relative humidity equal to absolute humidity of unsaturated vapor at room temperature divided by absolute humidity of saturated vapor at room temperature. So when your air is unsaturated, we know it is not completely saturated yet. It's not completely saturated yet. And if it was completely saturated, how it will be? I mean, we give it as a percentage, comparing it to the saturated state. We give it as a percentage compared to the saturated. So the first equation was based on absolute humidity. And the similar equation, that's a similar equation, almost same. Only thing we need to change is we need to replace the term absolute humidity with water vapor pressure. Okay, unsaturated water vapor pressure divided by saturated water vapor pressure, both at room temperatures. Those were the first 2 equations we learned. I said that if you can remember the first one, the second equation is just, it's a matter of changing absolute humidity with water vapor pressure. And then the third equation, it was about both should be in saturated state, but one is at dew point temperature and the other one is at room temperature. One is at dew point temperature and the other one is at room temperature. Okay, fine. So once again, the third and fourth equation were in terms of absolute humidity and pressure respectively, and then we summarize those 4 in this form. So these are the 4 equations we will be using today. Mostly we will be using the first one, and there will be instances where we might need to use the third one too, but most of the times in our past papers we will go with the first equation. What is the first equation? Absolute humidity of unsaturated vapor at room temperature. And don't forget the equation for absolute humidity. What is absolute humidity? Absolute humidity is mass of water vapor divided by volume. And then to quickly summarize what we did what we further did last week, this is about dry wet bulb thermometer. Dry wet bulb thermometer, it is an instrument we use, or apparatus rather, we use to determine relative humidity. And after we determine the relative humidity with the aid of the absolute humidity values of saturated vapor, or absolute saturated vapor pressure. So saturated vapor pressure data from tables, we can also find out the dew point. We can also find out the dew point. These were some of the questions we did. I hope. Yeah, these were some of the questions we did. Based on you'll need two tables to figure out the what do you call that, dew point. These are some of the questions we did last week. Okay, see. Yeah, and I'm not going to go into detail, you know what we did last week. I'm just summarizing everything we did. Right, with that being said, it's time for us to move on to our first our questions. But before that, I think it's better to have a clarity about certain aspects under absolute humidity and relative humidity. Last week we have also discussed about the experiment we perform to determine the relative humidity, or dew point rather, to determine the dew point at room temperature. So we discussed that experiment and added few additional points. We will need to answer certain questions. All right, so with that being said, let me discuss few more aspects regarding this. Otherwise I might forget. So what we're going to do today is graphs regarding humidity. We did not draw many graphs regarding humidity, I believe. So now let's focus on that. All right, so when it comes to graphs, about humidity, so let me start off with the graphs about humidity. Last week we had I think week before, not at the last class, the class before the last class, or one before the last class, we discussed about how humidity can vary when we change the volume of a system. Correct? How humidity can change when we change the volume of a system. Likewise, we are going to alter certain parameters, and we are going to see how those parameters can change absolute humidity and relative humidity. Okay, so today the first topic will be variation of absolute humidity and relative humidity with temperature. Before we start answering questions, I think answering past papers, it's better if we can have a idea about these parts as well, because there are questions based on graphs, right? So normally to plot any graph, we will usually increase the x-axis component. We'll usually increase the x-axis component, but here for a change, what we're going to do is we are going to decrease the x-axis component, that is the temperature, to see how the composition of that system varies. Now, first and foremost, let me start off with the system. Right, imagine you have a system with unsaturated vapor. Okay, this is the system, and yeah, first and foremost, you have unsaturated vapor. Now, when it comes to temperature, people, if you have an unsaturated vapor, what should we do to make it saturated? So let's say to start with, we are at, this is the unsaturated vapor. Unsaturated vapor. We'll write like this, no? Air unsaturated with what vapor? Air unsaturated with water vapor. Air unsaturated with water vapor. Okay, so if right, if air is, now the first variation we are going to learn is based on variation of absolute humidity and relative humidity with temperature. Remember, it's with temperature. So we are going to change the temperature now. Not now. I got an answer from one of you. It said what? Reduce volume, add more water vapor. No, yeah, those are the other things we can do. What we are going to do now is we are going to change the temperature. And how should we change the temperature to make this a saturated one? We have to reduce the temperature. So first and foremost, now this air is unsaturated with water vapor, and if I go inside the sample, let's say mass of water vapor inside it. Okay, listen to me carefully now. Mass of water vapor. I'll take the mass of water vapor to be equal to m. Mass of water vapor, let's take it m. Let's take it as m. That is a mass of water vapor in here. Now, what can you say about RH of this system, people? Relative humidity. Now, the volume of this system is fixed. Now, people, volume of this system is going to be fixed. Volume, let's say it's V. It's not going to change. It's a fixed volume, chamber of fixed volume, right? What can we say about the relative humidity of the system? Relative humidity of the system is going to be less than 100, isn't it? It's going to be less than 100. It's going to be less than 100. Relative humidity. Why? It is unsaturated. And furthermore, what about the temperature? What can you say about the temperature, people? Temperature. Let's say the temperature inside is theta. Temperature inside is theta. Okay. The temperature inside is theta. And what can we say about this temperature? The temperature here is definitely what? Less than, greater than dew point. Greater than dew point. That's why it is unsaturated. When the temperature of the system is greater than dew point, it is unsaturated. Then, just like I was discussing, to make it saturated, what should we be doing? We should cool down the system. Cooling down. Okay, somehow we are cooling down the system, right? When we cool down the system, let's see what's going to happen. So let me just copy this and paste it. Therefore, I don't have to rewrite everything. Right. Now I'm going to make the changes. Right. Now, when you cool down, at one point, what will happen? At one point, what will happen? Air just becomes saturated with water vapor. Correct? Air just becomes saturated with water vapor. When you cool down, air just becomes saturated with water vapor. And what about RH at this time? What about RH at this time, people? Tell me. What can you say about RH at this time? RH will become what? RH will become equal to 100, isn't it? RH will be equal to 100. That's when RH becomes equal to 100. And what can you say about temperature, people? What can you say about temperature? That's when the temperature, in fact, becomes equal to dew point. Temperature becomes equal to dew point. Good. That's when temperature becomes equal to dew point. All right. Yeah. And now, if you're wondering how RH is increasing, how is RH increasing? Let me explain that. Before that, I think we will add everything about this system. Everything. Now, let's write about AH. What is AH here, people? AH, anyone? If I write the equation for AH here, AH here will be equal to mass of water vapor, that is M, over volume of the system, V, M over V. And here also absolute humidity will be equal to mass of water vapor over V, because mass of water vapor will not change as of still it will remain in air. We are not adding water vapor or we are not removing water vapor. It's still there. Whatever the water vapor we had here, whatever the grams we had here, we will have the same amount here because dew is not yet formed. Air just becomes saturated with water vapor, and you can say dew at the verge of forming. No, dew at the verge of forming. It hasn't formed yet. It hasn't formed yet. Therefore, the mass of water vapor in the system is not going to change. It's going to remain constant. And that's the point where RH becomes 100, and that's the point where the temperature of the system becomes equal to dew point. And the absolute humidity, what is the equation for absolute humidity? That is mass of water vapor or volume. It will still remain constant, but RH is increasing. RH is increasing. It was a value less than 100. Now it has increased up to 100. Now, if you're wondering how RH changed, how is RH changing? What happened? So from here to here, people, how did RH change? So the two chambers have two different temperatures. Yes. Now temperature theta here, theta is higher value. Value is greater than dew point. Now the theta is equal to dew point. I'll say T. Okay, that's a good question. Right, we'll go for different values now. Theta 1 here, theta 2 here. Yeah, that makes sense. So let's take this as theta 1, let's take this as theta 2. I was trying to use theta as my variable, but it's okay, right? Otherwise it will be confusing both if you put theta for both. Now temperature has reduced, no? Theta 1 is greater than theta 2. We are reducing the temperature now. And what's happening during this time? We all know the equation for RH. What is the equation for RH, people? RH is equal to absolute humidity of unsaturated vapor divided by absolute humidity of saturated vapor into 100. When temperature is reduced, we have learned this value will decrease, and therefore this value will increase. I'll just within bracket I'll write when temperature reduced. We have learned absolute humidity of saturated vapor depends only on temperature, and when you reduce the temperature, that will reduce. So when the denominator of an equation reduces, the fraction should increase. And don't forget the fact that AH from here to here, AH is what? AH is a constant. AH didn't change. We didn't change AH. AH is a constant. See, M over V, that value is a constant value still. Absolute humidity. Right. Then moving on, after this, the important question now, what will happen after this? So what's going to happen after this? Yeah, if you cool down the system further, what will happen, guys? If I cool down the system further, what will happen? Then dew will start forming. That's the answer I was expecting. Yes, very good. Dew will start forming. Right. Let's paste whatever we copied earlier. Yeah, perfect. Dew will start forming, but the volume of the chamber will not change. Now the temperature is a new temperature that is below dew point, or temperature below dew point. So let's make it theta 3. Okay, and theta 3, guys, it's a temperature below dew point, because we have cooled down the system so that it has gone below dew point. And what about RH now? Let's do it step by step. Wait, and then let's describe this here. And I think mass of water vapor, I'm not going to give a fixed value now. Right. Yeah, then we'll describe the system first of all. No? The system has cooled down below dew point. System has been cooled down to a temperature below dew point. So what happens there is air saturated with water vapor and what else will be the observation? Dew formation of dew. That's a very important observation. Formation of dew. formation of dew is a vital point here. If dew is formed, what will happen to mass of water vapor? People, mass of water vapor reduces with time. Reduces as temperature goes down. Because as temperature reduces. Because dew is formed. Now we have dew at the bottom. At the bottom, or on the walls, whatever. I'll just put it in the bottom. We have dew. Right? And what about RH now, people? RH, since air is saturated, RH will be equal to 100. RH will remain 100 at 100, but temperature has gone down. And what about AH, people? AH, we know it's equal to M over V. For this scenario, AH is going to reduce with time. AH is going to reduce with time because mass is going to reduce. Therefore, AH will also reduce. But V is the constant. V is a constant. It doesn't change. It's the volume of the chamber. Volume of the chamber doesn't change. Therefore, AH starts reducing. RH will remain at 100. This is the summary of what happens when you reduce the temperature of a system starting from starting with air which is unsaturated with water vapor. We could have reversed it, but this is more, this gives you more clarity about it. Yeah, this gives you more clarity about it. Now what we need to do is we have to show this information in a graph. We have to show this information in a graph, and there are so many questions we can, not so many, there are a few, 2 or 3 questions in past papers where we'll have to answer based on this. So let me first of all start with the graph. I think this space is enough. If you have everything at one place, I think it will be easy for us to understand. Therefore, I'll draw the graphs here itself. Right. I know bigger the graph, it's better, but if you have everything with the description, the graph with the description, it will be much convenient to us, correct? So let's start with absolute humidity graph with temperature. Let me prepare the axis. Right. This is the variation of absolute humidity with temperature, theta. And we all know the reference point. Our reference point is going to be theta dp. Who is theta dp? That is dew point. That temperature is the dew point temperature. Right. Fine. So let me make a copy of this so that I can use the same frame for RH graph as well. Right, only thing I have to change is the A. Ready? All right. Is anyone willing to annotate this? Anyone willing to annotate on the screen? If you're willing to annotate, yeah, go ahead. What is the shape for the variation of AH and what is the shape for the variation of RH? Okay. Right. I can give you some time. Go ahead. So this is the explanation, theory part on the left side and the graphs on the right side for you. Hussein, you want to draw? I saw your name with the annotation. No. Okay, that is enough for Fahim's answer for absolute humidity. Right, good. Right, okay, right. I think she's finding it a little difficult to get a smooth curve. It's all right. Good job. Right. How about RH, Zainab then? Any idea about RH? Okay. I will share 2 diagrams in the WhatsApp group. Just downloaded those 2 from internet. I think those 2 were plotted using an experiment. All right. So those two diagrams, if you can see, they are the variation of AH and RH. Okay, right. So we have two graphs. Let's see. Yeah. Now you have to be a little careful here. We are doing this in reverse. Here the temperature is high. Here the temperature is equal to dew point. Here the temperature is low. So we have to start drawing the graph from right to left, not left to right, because we have started from a high temperature to low temperature. Because remember, among these values, among theta 1, theta 2, theta 3, which value is the highest value, people? Among theta 1, theta 2, theta 3, which value is the highest value? Theta 1 is the highest value. This is how the variation goes. Theta 1. So you have to start drawing your graph from right to left, not left to right. Okay, can you girls erase the graphs, please? Zainab Fahim and Zainab Hussain. Who is this? Right. Thank you. Now let's try to put this into a graph. The first part, AH, absolute humidity. Until now, we are from high temperature to low temperature. We are now when the temperature is greater than dew point, and until the temperature is equal to dew point. Until the temperature is equal to dew point, AH remains constant. Therefore, you will get a flat line like this for AH, people. There will be a flat line for AH. And from that point onwards, after that, when you reduce the temperature below dew point, as you keep on reducing temperature, dew will keep on forming and you will get a curve like this. This is how the curve will be. Because AH reduces. AH reduces. If you want, we can just put here this part of the graph. This part of the graph is when your temperature is greater than dew point. Apologies. When your temperature is greater than dew point. When the temperature is greater than dew point, no dew. Right? No dew. No dew. So AH will be constant. AH is constant. But when the temperature is less than dew point, as you can see, what happens? Dew deposits. So AH has to reduce. Because I have explained here, when dew is formed, mass of water vapor in air starts reducing because it is converting to liquid form. Okay, right. So let's be careful. I think normally what we do is we start and then we go, when we continue, we normally draw graphs from left to right. But here it's the opposite. We have started actually from here and going backwards. What about RH, people? What about RH? RH now. Talking about RH here until yeah, when the temperature is less than dew point, RH will be flat. RH graph will be flat because it will be 100 continuously. It will be 100. So you can draw a straight line graph like this, 100, and afterwards it will start reducing like this. Start reducing like this, and this value is 100. Now I know you will have questions with this part of the graph, but let me quickly finish this. 100% again. Here when the temperature is less than dew point, okay, the air is saturated with water vapor. But when the temperature is greater than dew point, unsaturated. Unsaturated. And remember, in this part, why do we have a shape like this? The reason is we know RH is equal to AH over AH saturated into 100. So when you reduce the temperature, when temperature is reduced, sorry, when temperature increases, apologies, when temperature is increased, AH saturated will increase. It's not very clear. Let me rewrite it. AH saturated. Here AH saturated into 100. So when you reduce the temperature, sorry, when you increase the temperature, absolute humidity of saturated vapor also increases. That's why RH reduces. And we know When the denominator increases, this is how the fraction is going to reduce. That's why this shape. Okay, people. Right. So until you reach dew point, the value of RH will keep increasing until 100, and then once your temperature is below dew point, your air is always saturated. Therefore, RH will remain at 100. Okay. So if you understand these two graphs, it's going to be easy for you to handle questions regarding graphs. All right. So this is the first variation, that is variation of absolute humidity and relative humidity uh, in terms of who? In terms of temperature. In terms of temperature. So I hope you guys understood it. I've explained you step by step as to how it happens. Even if you can't remember the shape of the graph, what I personally feel is you can still figure out. How it's going to be. Still figure out how it's going to be. Right. And then it's time for us to move on to the next part. That is the variation of AH and RH with volume. All right. Once we do that, we can move on to the next part. Right. So that's the next topic for today. Variation of AH and RH with volume. And remember, once again, with volume at constant temperature. At constant temperature. We are going to change only the volume. And in the previous topic, I missed something. Wait, let's add that to the previous topic as well. The previous topic, what should I add, people? Variation of AH and RH with temperature at constant what? Volume. Here we didn't change the volume, no, people? We didn't change the volume, correct? Yeah, so let's add that also here. Sorry about that. Variation of AH and RH with temperature at constant volume. That's the topic. That should have been the topic, because it was a chamber with fixed volume, right? And now let's move on to the next part, that is variation of absolute humidity and saturated humidity with volume at constant temperature. Earlier it was constant volume, right? This time around I will have to show the change in volume. So let me start with a large chamber or something, and chamber can be, the volume of that can be changed somehow. Okay, we can change the volume of that. That's a basic idea, right? Sorry. So I'm going to make some copies. There are around 3 copies of this, and I'm going to show that the volume is decreasing maybe here. Right. Apologies. So you can see the volume has reduced a little bit, and then let's make another copy of that and paste it here and reduce the volume further, right? So you can clearly see how the volume is reducing. Good. And this is what's going to happen, and now we are going to analyze the process. Volume reduced and volume reduced further, but remember the temperature is constant. Okay, so here if I take the temperature to be theta. Here also temperature is theta. Here also temperature theta. Temperature theta. Okay, right. Now temperature theta, temperature theta, temperature theta. We are now maintaining the system at same temperature, and initially, just like before, I'll take the mass of water vapor inside. Okay, mass of water vapor inside, we'll take it as m initially. And to describe this system, what can I say? This is a system where air is unsaturated with water vapor. Air is unsaturated with water vapor. Right. And if the air is unsaturated with water vapor, people, what can we say? Two things. We can say two things. One is RH is less than 100, is it? RH is less than 100. And what can we say about the temperature theta and the dew point for this? Now, we'll discuss another point also, that is dew point. This system will have a dew point, people. This system will have a dew point. I'll take that dew point as theta 1. Because we are not changing the temperature of the chamber, we are maintaining at theta. Please tell me about theta and theta 1. Who is the bigger value? Is it theta or theta 1 now? Earlier, dew point doesn't change. In the earlier system, dew point will remain constant. Dew point will remain constant, but now dew point is going to be different. Let's see. What is it? Who is the bigger value? Theta. Exactly. Theta will be the bigger value. Because when the temperature of the system is greater than dew point, it will be unsaturated. It will be unsaturated. So as you keep reducing the volume at one point, what happens? Air becomes just saturated with water. Air becomes just saturated with water vapor. Air becomes just saturated with water vapor. And at that point, what will be the mass of water vapor, guys? Still, it will be same, no? Mass of water vapor will still remain same. Mass of water vapor, it will be m, no change. But now the dew point will be different. Now the dew point will be different because we are changing the composition of air. We are changing the absolute humidity. Dew point will be equal to theta 2. Theta 2. And I'm forgetting another important point, that is the volume of the system. Because we are changing the volume, right? We are changing the volume. I'll take the volume here as V1. And here this volume is a special volume. Therefore, I'll give it a special symbol V0. Because that is the volume where the air becomes just saturated. That's the volume where air becomes just saturated. So absolute humidity, just like the previous case, if I write the equation for absolute humidity here is equal to m over v1. And how about RH, people? Now RH, relative humidity, as air becomes saturated, RH will become 100. RH will become exactly 100. And at that point, what can you say about the dew point and the room temperature? Dew point and room temperature now are going to be equal to each other. The room temperature now becomes the dew point. So dew point is varying. And what about absolute humidity, people? Absolute humidity here is equal to m over v2, and it's obvious m over v0. It's obvious that v0 is less than v1. So from this point to this point, what is happening to absolute humidity, people? Absolute humidity is equal to mass over volume. The volume, it is the volume is decreasing. Volume is decreasing. If volume decreases, absolute humidity has to increase, because mass of water vapor, it is constant. Dew is not formed yet, no, people. As long as dew is not formed, m will not change. All right. And afterwards, if you reduce the volume further. Now that air can't take any more water vapor in it. Now the thing is this, now here it has water vapor. Now you are compressing the system, so now water molecules in the vapor phase, they are getting congested now, too congested. If you reduce the volume further, that air can't have them all so close to each other. Then what happens is, what will happen? Dew will start forming after that. Dew will start forming after that. So we'll have dew here. And what will happen to mass of water vapor, guys? Mass of water vapor will reduce. Mass of water vapor reduces as dew forms. And now the volume is, sorry, V2, let's say it's just V2, whatever. Right. What about air? Air is saturated. Air is saturated with water vapor. More importantly, dew starts forming. So dew formation. And talking about RH now, what is RH? RH is still going to remain at what, people? 100, yeah? RH is still going to remain at 100. And what can I say about the temperature now? Dew point. What can we say about dew point? Yeah, now the temperature is, dew point is, wait, no. If you take the dew point for this system, dew point for a system is theta 3. If the dew is forming, that means theta should be less than theta 3. Dew is forming, no? If theta is equal to, if the temperature is equal to dew point, it just becomes saturated. Dew at the verge of forming. Dew at the verge of forming. Remember that. If dew is being formed, that means the temperature of the system at that instance is less than the corresponding dew point, people. Corresponding dew point. So it should be less. Okay, and how about AH now? What about AH? Now I'm going to ask you a very important question. What about AH? What will happen to AH? Anyone? AH is equal to AH what? Saturated now. AH is equal to AH saturated. AH saturated is constant. It will not change as long as temperature is constant. Do you understand that? Now I know you have some questions because we have reduced the volume, true. We have reduced the volume, true, but M also has reduced. Both M and V both have reduced. AH is equal to AH saturated. Now AI is saturated here. Now AI is saturated here. Once AI is saturated, and we are reducing the volume. When we reduce the volume, we are not changing the temperature. Earlier we changed the temperature. Here, we change the temperature. So absolute humidity can change there. But here, absolute humidity, once it becomes saturated, if you don't change the temperature, it can't change. So I'll explain that. Wait, I'll explain that further. I know you have some doubts about that, but I'll just quickly explain it. Once air becomes saturated with water vapor, as long as temperature is not changed, absolute humidity of saturated vapor will not change. Saturated vapor will not change. Wait, like density and pressure change in yeah, something like that. Okay, now guys, listen, If you are wondering what's going on here, from here to here, from here to here, I know you have problems about AH now, right? AH is equal to mass over volume. Remember, both are reducing. Do you agree with me or not? M is reducing. Why? Dew is formed. And V is reducing because we are reducing the volume of the chamber. Do you understand? Oh, I think it's... No, wait, I think it's too congested. There, I'll write it. Where should I write it? Is that clear? Okay, I'll put it. I'll put it here. Never mind. Okay. From once it becomes saturated, once it has become saturated, you can say this. I know AH is equal to mass over volume. Most of you now, I got few answers saying AH will what reduces. AH will reduce. Yeah, that's because you are thinking just like the previous one. Here, if dew is formed, AH should reduce. But earlier people, volume was constant. No, volume was constant. Now, volume is not constant. Volume is also reducing. Both are reducing. M is reducing. Why? Because dew formed. Volume is also reducing because volume of chamber reduced. Then considering both, we can say what? Considering both, we can say now I don't think that's the best argument, to be honest. I don't think that's the best argument, to be honest. This is the best argument. What I have written in purple is the best argument for that. But if you want to explain that using the equation, this is it. So AH remains constant. After clear? And Hafsa, I don't know. They are the ones who raised the question. I hope now it's clear. So then AH of second and third situation the same. Yes. AH of second and third situation the same because Hikma, it's saturated, it's saturated. The system has become saturated. Okay. Saturated with water vapor. This system is saturated with water vapor. This system is also saturated with water vapor. For a system which is for a sample of air which is saturated with water vapor, if you don't change the temperature, absolute humidity of saturated vapor will remain constant. That's what we have learned, right? Absolute humidity of saturated vapor depends only on temperature. It doesn't change with anything else. Here we change the temperature. That's why it changed. So then the dew points in both situations also same. Dew points will be same, no? Will the dew points be same? Dew points. Good question, that one. Dew point. Absolute humidity won't change. Dew point. What can we say about dew points? Absolute humidity. I'm 100% sure that absolute humidity is not going to change. It can't change. It will be constant. There's no argument in that because it has become saturated and the temperature is not changing. But dew point, that's something we will have to ponder because dew point depends only on absolute humidity, people. Dew point depends only on absolute humidity. It doesn't depend on anything else. If you don't change the absolute humidity, dew point will not change. So absolute humidity, the composition of air, the moisture content inside the system. That's what affects the dew point. Theta. So what can it? But normally when the dew is formed, the temperature should be less than dew point. That's what I was saying. That dew point here must be greater than the current temperature. But on the other hand, dew point depends on absolute humidity. Wait, I'll check and let you know about this dew point theta 3, whether it's equal to theta or less or greater than theta. Yeah, mass of water vapor is changing, true, but it's not about the mass always. It's about is it about the mass, or is it about the mass per unit volume? Wait, I'll come back to that. Theta 3. Now we have a question about theta 3. I'll come back to that. Yeah, but my gut feeling says theta 3 should be greater than theta if dew is forming. So the mass of water vapor constant here. The mass of water vapor is changing, but at the same time, volume is also changing. Uh, the theta 1, theta 2, theta 3, they are the dew points for these samples. We are not changing the temperature of the sample, remember. Okay, this is a sample, this is a sample, this is a sample, because we are changing the conditions now. So for a given sample, the sample will have a normal temperature. You can just measure that using a thermometer, and that sample will have a dew point, right? So if the sample is unsaturated, the temperature of the sample is greater than the corresponding dew point. If the sample has just become saturated, the temperature of the sample will be equal to dew point. If the sample is saturated and if dew is formed, the temperature of the sample should be less than dew point. That is how it normally works. Fine. So for the time being, I think this should be the case, but I'll get back to that. In case if we need that idea about dew point, we'll get back to that. Okay, fine. So guys, this is the basic idea about how relative humidity and absolute humidity change with change in volume. Okay. So when you reduce the volume, these things will happen. And again, we have to start from, when you draw the graph, we have to start from we have to move from right to left, because from high volume to low volume. Let me start the graphs then quickly. Yeah, let me start the graphs. Yeah. Graph. Yes. Now to plot the graph, let's start with the axis, just like before. This is the graph for absolute humidity, and here we have the volume of the chamber. Okay, volume, and we have a reference volume. Earlier, when it comes to temperature, it was the dew point, but here it's the volume at which air just becomes saturated, and I have marked it as V naught in the flow chart. So I will go with the value V naught. Okay, let's make a copy of this, because we have to draw the same graph for RH with volume. Yeah. Okay, people, just one small change, that is making AHRH. Okay, again, anyone willing to annotate? Think carefully and do. Zainab, shall I try now? Is she there in the class? Yes, she's there. Should be there. Go ahead. Shall we give it a try now? Okay, that is Zainab Hussein, right? Zainab Hussein. Yeah, okay. Zainab, okay. Others also can try. Anyone else willing to draw? You also can try. All right. So, okay, Zainab, can you get rid of that? Thank you. Good, very good. Yeah, the graph for AH. Now, the graph for AH, how will it be? As you can see, when the volume is less than V naught, when the volume is less than V naught, here the volume is less than V naught, no? AH is constant because it's saturated. Temperature is not changing. As long as temperature doesn't change, when the air is saturated, here here we know our volume. Oh, sorry, our volume is less than V naught. That means saturated. We are talking about a saturated sample. Air saturated with water vapor. If air is saturated with water vapor, as long as temperature doesn't change, AH will remain constant. And when you increase the volume further, what happens? Volume increases, and AH should, from here to here, AH should increase. So there the graph is going to be, now when you increase the volume, AH should reduce, no, people, here. So the graph will be a curve, say a curve like this. Now V is greater than V naught here. Sorry. V is greater than V naught. So it is actually unsaturated. Unsaturated. It won't be a straight line. It should be a curve. Can't be a straight line. Why curve? Wait, here. Absolute humidity, it is equal to mass over volume. Absolute humidity is inversely proportional to volume. Inversely proportional to volume. So when it is inversely proportional to volume, it should be a curve, right? Like Boyle's law graph. Agreed? When you increase the volume, this is the m is constant. M is constant because du is not formed. So when your volume is greater than V naught, m doesn't change, mass of water vapor. So when you increase the denominator, the fraction reduces this way. It can't change what in a straight line form. Understood? Can't change as a straight line. It should be a curve like this. Careful, huh? And then how about RH, people? How about RH? RH, surprisingly, will also have the same shape. RH will also have the same shape. Why? Look, when the volume is less than V naught. When the volume is less than V naught, the system is saturated. If the system is saturated, what is RH? RH is 100. When the system is saturated, RH is 100. And when the system is unsaturated, RH will reduce like this. I will explain why. Don't worry. So here, when you the value here is 100 percentage. The value here is 100 percentage. Okay, and here V is less than V naught, so AI is saturated. When the AI is saturated with water vapor, we know RH is going to remain 100. And here, when volume is greater than that V naught value, it is unsaturated. Unsaturated. And what is the equation for RH? We have to focus on. Listen to me carefully. RH, it's equal to AH over AH saturated into 100 people. So when the volume is greater than V naught, AH is reducing, but AH saturated is constant. Tell me, AH saturated is constant. Why is that? This is going to be a constant value. This value is going to be constant. AH saturated is going to remain constant. Why? Constant temperature. This is constant. Huh? Constant. Because we are not changing the temperature. As long as we don't change the temperature, AH saturated is going to remain constant. But when you increase the volume, we know AH is going to reduce. So RH will reduce just like the reduction in AH. Here, AH is reducing. RH will also reduce that way. So both the graphs will have the same variation, same shape. But the previous one, it was not the same because it was the variation of AH and RH with temperature. This time it's the variation of AH and RH with volume. Okay, so don't try to buy hard this. Don't try to buy hard this. Try to understand it logically, like I have explained it. Then it will be easy for you. If you try to just buy hard this, then it will not make sense. Even if you have forgotten the shape, if you have the understanding of the what do you call that, the basic concepts, then still you can figure out the graph at the exams. Even if you have forgotten the shapes. Okay, so let's try to focus on this. So I'm not going to repeat it over and over again. We did a record. What do you call that? The class is being recorded, so you can, if you have any confusions, you can rewatch it and get it clarified. Because we have spent all this time. Okay, we have spent all this time to get these 4 graphs. Imagine just for these 4 graphs, we have spent such a long time, but I hope it's worth it. Okay, right. So yeah, let me take a screenshot of this. And yeah, these were the things I wanted to explain before we start questions, people, because we hadn't done this in the class last week, theory part, right? And now the next thing I want to discuss is this. The next one is question. I can remember a question like this from the past paper. Yeah. So let's start. Let's try that question out. Okay. Let's see who is going to handle this carefully. Question is, an AR sample is initially an air sample is initially unsaturated with water vapor. Unsaturated with water vapor. Air sample is initially unsaturated with water vapor. The volume of the chamber is reduced. The volume of the chamber is reduced while maintaining constant temperature. Right. The sample becomes saturated with water vapor. The sample becomes saturated with water vapor when volume is equal to V naught. When volume is V naught. Volume of the chamber is V naught. Plot the following curves. Plot the following curves. You have to draw two graphs now. Number one, pressure versus volume. Pressure versus volume. Pressure means P versus volume. V. Second graph, PV versus volume. PV, the multiplication, Boyle's law multiplication, P into V, that versus volume. Okay, right. So these are the two graphs we are going to plot. Shall we give it a try?